Registro su questo. Okay, so thank you very much for coming, and I will say, okay, Becky, now is your time.
Great, thank you so much. Thanks, Sergio, for that really nice introduction, and thanks everyone for being here. It's really a pleasure and a privilege to share my research with this audience. I might step to the side here just a little bit. So it's great to see you. Now you're not going to see me anymore. There I go. How's that? I want to start with a few thanks and begin by acknowledging many students and colleagues who have contributed to a number of collaborative studies in the yes, we want to.
I want to.
You can make that go away. Here, this up here, I think. If you click that.
Yeah.
Oops. Ah, nice. That's
I don't
good.
know if I can.
I think that's going to be fun.
Okay.
Oh.
Let me.
Oh. I don't know. Full screen? You're in full screen, right?
Yes, I am already in full screen, but.
I think maybe that might just disappear. I think that'll just go away once I get started.
Okay, okay.
We'll see, hopefully. There's not too much content at the very top of the slides. So it's really, like I said, a great pleasure to be here. And I wanted to start by acknowledging many students and colleagues who have contributed to collaborative studies in the Salton Trough and the Gulf of California over 20 or 30 years of research. And there are too many people to list here, but it really takes a team, and the collaboration has been great for the science, as well as really gratifying just to work with such an excellent group of collaborators. Especially grateful to Sergio Longitano for inviting me to come here and providing such a rich experience for learning and doing research here in Southern Italy. I've learned so much, it's just been amazing. I'm also grateful to the Department of Sciences, who is hosting me at the University of Basilicata, and also thanks to the Italian Geological Survey Society for sponsoring this event. So it's really a privilege to have an opportunity to share my research with this audience, and I really welcome input and feedback and questions either during or after the presentation. So as the title of my presentation says, and I'll go ahead and start with the title. Today I'm going to talk about the tectonic controls on development of a large river delta system at an active strike slip margin, looking at the San Andreas Fault and the Colorado River system. And so the goal here will be to really emphasize the importance of tectonic controls on the development and early evolution of a large river system. And our case study will be the Colorado River and its interactions with the San Andreas Fault and the Eastern California Shear Zone. And what I'm going to show you today is evidence that these fault systems exerted a very large influence that led to variable rates of subsidence and changes in relative sea level within basins, fault-controlled basins, and that those tectonic processes also resulted in trapping of sediment in fault-bounded basins, which in turn produced very large fluctuations in river sediment discharge, which in turn resulted in the very rapid regional scale back and forth migration of the Colorado River Delta. Now, I should emphasize that some of these conclusions are unexpected. We have some surprise factor here. And as a result, they're also a little bit, in some circles, still controversial. And so I really welcome questions and input and feedback or any perspectives that the audience might bring to bear. So just a quick outline on how we're going to tackle this this content. Of course, you see here on the right-hand side is a map, a very simple tectonic and topographic map of Western North America and the San Andreas Fault system, as well as the Colorado River catchment. And I'll be describing this map in a few minutes. So today, what I'll do is I'll start with some concepts, some key concepts in source to sink and sediment routing systems, and then I'll introduce you to the Gulf of California and the Salton Trough transform rift margin. Then we'll take a look at the stratigraphic record of the initiation and early evolution of the Colorado River. And what I hope you take away from this presentation is just the kind of basic idea that faults can and do exert a very major influence on the dynamic behavior of large rivers and deltas in tectonically active settings. So we have really good evidence for that here, and we should expect to see those kinds of dynamic interactions occurring in other types of tectonically active settings. So this slide shows a few graphics related to the source to sink dynamics and sediment routing systems. And let's see, so there's the, let me get that cursor going. So in this left-hand graphic from Allen 2008, it's just a colorful 3D depiction of how sediment moves from an eroding source through what we often call the transport or the transfer subsystem through a river system into its final resting place in a depositional sink with these particle pathways along the river. And the source to sink is a very strong concept that drives a lot of research now, and it's a very resilient and important concept for stratigraphic studies. Now, it looks like the label here is still covering some text, but don't worry, I'll tell you what it says. The graphic on the right-hand side is a figure from Michael et al., which depicts an example of a sediment routing system from an Eocene basins in the southern Pyrenees. And they used evidence from stratigraphy and sedimentology to reconstruct the sediment transport system within a river channel network right through from several eroding sources. And this diagram shows the sediment discharge represented by arrows entering a transport system or river network. And then it shows the sediment discharge is represented by the arrows, and the red boxes represent the extraction or the removal of sediment from that discharge as a result of deposition. And the basic concept here is that we can have sediment discharge is like water discharge. It's a volume per time. It's a flux rate. And if we have sediment getting fluxed or discharged down a river channel network, then any deposition that occurs along that pathway will extract, it will remove sediment from the discharge. And so sedimentation that occurs within these basins has the effect of reducing the discharge in the downstream direction because the sediment is extracted by deposition. And so if we add faults into this picture, we know that faulting in general, often there are different ways and different styles of faults that produce subsidence in sedimentary basins. And so we can expect that tectonic subsidence along a river network will enhance the deposition of sediment, and therefore can be expected to increase this effect of sediment trapping, and all sediment which will be deposited will be removed from the load, and that will cause a decrease in the discharge in the downstream direction. Now, to amplify on that concept is a diagram that I created recently, which is just another way of sort of showing the same concept. There's been a lot of research on this over the years, some really important papers by Chris Paola and Paul Heller, Phil Allen, and many others who have shown that this river sediment discharge system can be represented as a mass balance where if we obey some basic rules of conservation of mass or volume, then we can see that the subsidence in a fault-bounded basin, if we hold the elevation constant, then the only way that you can hold elevation constant with a basin subsiding is to keep filling it up with sediment. And so if your subsidence, your tectonic subsidence causes the crust to sink down, but the elevation is not changing, then that will absolutely cause the trapping of sediment. And that can be modeled as a conservation of mass or a diffusion problem where the rate of tectonic subsidence represented over here, the vertical rate of subsidence, is proportional and can be set essentially with some rigorous development of river discharge equations, can be said to be proportional or scaled to the downstream difference or decrease in sediment discharge. Another way to say that is that the downstream change in sediment discharge is directly proportional to and is forced by simply the rate of subsidence. Okay, and so we can expect this to have an important control on the development of large rivers in tectonically active settings, and we'll see how that happened in Western North America. Now, so here is a regional view of the Pacific North America plate boundary in the Western North America. And this is a major, as many people are familiar with, is a major dextral right lateral strike slip transform margin, which initiated about 25 million years ago and has been growing and evolving since that time. Now, the modern configuration of the plate boundary includes the San Andreas Fault in the north, which goes through the Big Bend here and into the Salton Trough, which I'm highlighting here, and then it continues down into the Gulf of California in the south. So we often think of the San Andreas Fault as the Pacific North America plate boundary, but actually it's really just the northern half of the Pacific North America plate boundary, and the Gulf of California with its long transform faults and short spreading centers makes up the southern half of that plate boundary. Now, the Colorado River is the fourth largest river catchment in the conterminous US. It has a catchment area of 630 square kilometers, so it's quite a large catchment. And it is the major source of water for many states in the southwestern US, which are currently really struggling with the challenges of the current climate change and mega drought in that area. And it's a very difficult problem, which for which there's no obvious immediate solution. Now, if we look at the sediment discharge for this river system, prior to the installation of dams in the early to middle 1900s, the river discharge was about 150 to 200 megatons per year, and it was at that average value over 5 million years of time. So this is a very large discharge compared to global rivers. And you might expect, well, does that require a large erosion rate? And it doesn't really, because at just moderate erosion rates of say 100 meters per million years or something, which is the average up here in the catchment, if you just do that over a very large area, then your volumetric discharge at the lower end, it can be quite large. And that's what we see here in the Colorado River system. Now, after the construction of those dams and reservoirs in the middle 1900s, the sediment discharge decreased by 3 orders of magnitude to roughly 0.1 megatons per year. And this is important both in terms of the health of the delta at the northern end of the Gulf of California has really been decimated by this loss of sediment. And this is the construction of dams was the single reason why there's been this huge decrease in the river discharge just in the last 100 years. And it's also important for us to think about how that might happen at geological timescales in the past. Okay, so let's take a look at the Gulf of California, and this slide helps to sharpen kind of our understanding of the plate boundary as a sort of an oblique transform rift plate boundary. And what you can see is that the white arrows represent the relative plate motion, but you can see that the overall trend of the Gulf of California is not exactly parallel to the relative plate motion. It's these long transform faults that are are parallel to the relative plate motion. And so because there was a volcanic arc along this trend in the past, that's where the crust broke, the lithosphere broke when you start opening up the Gulf of California. And so that results in this being a largely transformed plate margin with a slight component of obliquity, which results in the opening up of these little pull-apart basins, which have evolved into oceanic spreading centers. Now, in the present day, we see deeper water in the south. The basins become shallower toward the north and very shallow to non-marine in the north, which can be described as a change from sediment-starved to filled and overfilled basins. And this change in the map pattern is entirely the result of voluminous input of sediment from the Colorado River over the last 5 million years. So without that sediment input, the basins in the north may very well look just like the basins in the south. Now, so this large input of sediment from the Colorado River has actually exerted a fundamental influence on major aspects of the rifted margins, such as rift architecture and crustal composition and processes of lithospheric rupture. So once we understand that from almost like the static view that you see in this picture, then we can go on to ask, how did that start? What was the engine that created that whole delivery of crust eroding out of the crust and being transferred down into the plate boundary? And what were the major processes that controlled the initiation and early evolution of the Colorado River in early Pliocene time? And so to study those questions, we have moved our focus north, and the map on the right-hand side here shows just a topography fault and the course of the lower Colorado River here through a mountainous terrain right into the Salton Trough. So this area is the Salton Trough. It's a lowland. The mouth of the river is right here at Yuma. Sometimes the river sends sediment south into the Gulf of California, and then sometimes it switches to the north. And in fact, that's how the Salton Sea was filled up with water, was because of a channel that was breached during a flooding period, and they lost control of it, and a desert valley below sea level filled up with a glistening lake, and it's now it's drying out. Okay. So within this setting, we have, again, these are the faults of the San Andreas Fault. There's the San Andreas Fault proper. We have splays of that fault, the San Jacinto and the Elsinore faults, and all those faults feed down into the Cerro Prieto Fault, which is the major transform at the north end of the Gulf of California. So just recall that the Pacific plate is moving out to the northwest relative to North America. And then over here, we have the Eastern California shear zone, which is an important part of this story. It's a large region of diffuse transtensional deformation, lots of strike slip faults, normal faults, some areas of transgression as well, and all linking over here to the State Line Fault and then the major faults in the Death Valley area. So to study the initiation of the Colorado River, we've spent about 10 years now looking at the 5 to 6 million year old Bowes Formation, which formed in a series of lakes in the north and a shallow sea in the south. And our research has been focused here in the southernmost Bowes Formation in the southern Blithe Basin. And in addition, we have some older results from study of the Fish Creek Biocito Basin over here on the western side of the Salton Trough. So you see the Fish Creek Biocito Basin is actually traveling on the Pacific plate. So it has been moving to the northwest through time. When we remove 5 million years worth of that tectonic translation, we can see that the Fish Creek Biocito Basin originally formed down here south of Yuma. Well, this was the position of the basin at 5 million years ago. It actually first originated maybe 8 million years ago. So it has been translating, excuse me, all during that time. So what I'm going to do is I will first show you some highlights of the stratigraphic record of river initiation in the western Salton Trough, the Fish Creek Biocito Basin, and then we'll switch back over here to the southern Bowes Formation, and then we'll try to integrate that whole story into a picture of what happened over time during that river initiation. So this is a geologic map of the Fish Creek Biocito Basin, and a few things to highlight here. First of all, this is from prior work by Charlie Winker, Gary Axon, John Fletcher, and some really important early studies. And the first thing you might notice is all this red color over here represents Cretaceous and older crystalline and plutonic rocks that lie in the footwall of the West Salton Detachment Fault, which is this fault that I'm tracing here with the cursor. You can see that here, yeah? So this is a low angle normal fault, or what we call detachment fault, which was active during deposition of the late Cenozoic section, which you see here in all of these different colors. And then later, the detachment fault became inactive with the initiation of these younger strike slip faults. So now the detachment fault is all squirrely and twisted and folded around because it has been overprinted by younger strike slip faulting and related folding. So initially this was a smoother fault with a more simple trace, and it formed a major basin bounding fault at the western margin of the Fish Creek Biocito Basin. Now the pink color here are the similar rocks, but in the hanging wall or the upper plate of that detachment fault. And then all of the different colors that you see here, the orange, purple, yellow, blue, green, and so forth, are all the sedimentary rocks, which we'll be talking about. And the sedimentary rocks are preserved in a southwest tilted, large scale tilt block With the tilting toward the southwest, that means that the oldest part of the section where it rests on the crystalline basement rocks is up here in the northeast. And then as we travel to the southwest, we're going up section into younger and younger deposits. This is a distance of about maybe 15 or 20 kilometers with uniform bedding dips, which gives us like a 5.5 kilometer thick section. And you restore that back to horizontal, you have 5.5 kilometers of stratigraphy in this basin. And today I'm going to focus only on the lower half of this section, which is indicated with the red line there. So just remember, we've been able to put this together by mapping and measuring in a lot of detail the southwest dipping sedimentary rocks. So this is a column from our 2011 paper with a number of colleagues here that shows the lower half of that 5 kilometer thick section. We have 2,500 meters of section represented here, showing late Miocene to early Pliocene sedimentary deposits of the Split Mountain group, Imperial group, and the Palm Spring group. And we can see here that we have a very good control on the age, the depositional age of these sediments based on extensive and years of work on paleomagnetism, as well as uranium-led tuff ages higher in the section. And I didn't list it here, but also very important to this study is additional age controls from marine micropaleontology and biostratigraphy. So we have multiple age controls on the age of this section. And what I'm going to do is walk you through the main key features of this section, starting with a depositional contact on top of those older crystalline basement rocks, and a coarsening upward section from sandstone to conglomerate and breccias, which accumulated in the proximal alluvial fan setting during the initiation of those faults that created that basin. And then at the top of that, there's an abrupt switch to marine turbidites. And we can start stepping through that. So here's our marine turbidites that come in at about 6.3 million years ago in the latest Miocene. And then overlying that is a really important sandstone unit called the Wind Caves member of the Latrania Formation, which contains the oldest known deposits of the Colorado River that accumulated right here in this basin. Remember our location. This map over here shows the location of the study area. Now, going up section, then the Wind Caves member is overlain by the Coyote clay, which is a marine claystone, which you can see highlighted on the map with this blue area, this blue line that schematically shows the distribution of the Coyote clay. It's a very widespread regional claystone unit. And then that is overlain by marine rhythmites, which shallow up into shallow marine deltaic deposits, and finally culminating with the deposits of the Arroyo Diablo Formation, which represents the earliest river deposits, or I should say, yeah, the first arrival of the river environment in the Salton Trough at about 4.2 million years ago. Now, so I'm going to just show you a few highlights from the Wind Caves member, the Coyote clay, and the Arroyo Diablo Formation to show you what those rocks look like. And this is a nice photo of the Wind Caves member, which formed in a submarine canyon. And it consists of thick-bedded turbidites that form in these large channels. And it's a pretty dramatic example of really thick-bedded, sand-rich turbidites that accumulated by large, high-density turbidity currents in a submarine channel complex. And you can see the detailed measured section over here on the left. You can see there's an abrupt start of the Colorado River sand within this thick-bedded turbidites right here. And then going up section is a gradual transition. And at the top, we get back into the Coyote clay. Now, the Wind Caves member contains distinctive sandstone, petrographic, and detrital zircon signatures that clearly identify it as being derived from the Colorado River. And underneath that, we have only locally derived sandstone. And here is a paleogeographic reconstruction for the deposition of the Wind Caves member in the Fish Creek Biocito Basin down here about 5.3 million years ago. And this reconstruction is based in part on the data from Charlie Winker's really great work in this area. And he found very consistent southward transport in these submarine sandstones. And this essentially was a small submarine fan which formed at the end of a long submarine channel or canyon system, which had the small delta at its north end. So we can use this kind of information to actually calculate the paleo sediment discharge for this deposit by estimating the volume of the sediment in the wind caves member, as well as other age equivalent deposits in the Yuma area, and also knowing the duration of time over which this unit accumulated. And I won't really spend a lot of time on the details, but we can use these basic values and estimates to estimate the discharge at that time. The sediment discharge at that time was roughly 6 to 20 megatons per year, which is a nice average for lots of rivers, but is actually much less than the long-term average for the Colorado River, which was like 150 to 200 megatons per year. So that will come back into play. We'll hang on to this idea that the earliest Colorado River, although it made a dramatic appearance in the basin, it started out with a relatively moderate or weak sediment discharge. Okay, so going up section, then here's this reference section that we saw again on the left. The wind caves member is gradationally overlain by the coyote clay, which you see here in this field shot, and we saw earlier on the map, is a widespread regionally extensive, ultra fine grained sand-starved marine claystone. There's like hardly even any silt in this unit. It's almost completely clay. It's very fine grained, and it does record, as far as we can tell, based on all of our evidence, it records the very effective shutdown of sand delivery from the Colorado River at about 5 million years ago. And in fact, this is similar to other examples of sediment shutdown that have been documented for ancient submarine fan systems, including thrust top basins in Italy and offshore borderland basins in California and submarine fan system in the Kura Basin. So we think we've got a really great example of that right here. Now, remember then going up section above the coyote clay, we have a resumption of sand input and there's prograding deltaic shallow marine sequence, which is beautiful, but I don't have time to show that to you. And it culminates through like 1,000 meters of section. Finally, at the end of this thick, coarsening upward, shallow marine deltaic succession is the arrival of the actual deposits of the Colorado River. And we'll see that in the next slide here. That's the Arroyo Diablo formation of the Palm Spring group. And these are really beautiful, large-scale cross-bedded sandstones and overbank fines that record the arrival of that river system in the Salton Trough at about 4.2 to 4.3 million years ago. And this is our reconstruction for the river as it arrived into the Salton Trough at about 4 million years ago. And from other work, we have, oh, by the way, I should just point out that here's the West Salton Detachment Fault in our reconstruction. And this is actually an example of, it might be sort of the result of kind of a type of strain partitioning where we had the dominant strike slip motion on the San Andreas Fault at that time. But because it is an obliquity of the regional strain, then the extensional, the transtensional component was taken up by slip on this low angle normal fault, this detachment fault, resulting in this kind of two-sided basin with a strike slip fault on one side and a low angle normal fault or detachment fault on the other side. And I don't have nearly the time to show you the evidence for how we're really very confident in this fault geometry, but I'd be happy to discuss it later. So in any case, other data show that the Colorado River, the actual river itself, prograded, now the delta and then the river, prograded into the basin during a time of abrupt increase in the subsidence rate, and then the fluvial conditions persisted in this basin during rapid subsidence. And that's actually opposite of what you'd expect, because if the subsidence rate increases, then that should really push the delta back toward the source. But in this case, that didn't happen. So by the time we get to 4 million years ago, then we've probably switched into this very large discharge. I mean, the fact that that happened requires a large increase in the sediment flux rate. And that's consistent with our estimate for the long-term discharge of 150 to 200 megatons per year. And this behavior has actually been documented in other supply-driven delta systems. So I've walked you through a few of the key elements of the record in the Salton Trough that shows us some of the important events that happened during the initiation and then early evolution of the Colorado River. And now I want to switch and look upstream at the correlative record in the lower Colorado River Valley. We saw this map earlier. Again, here's the lower Colorado River. And so now let's take a moment to look a little more closely And so what we're going to do is take a look at the Bows Formation, which is roughly dated between approximately 5 and 6 million years old, and it formed in a series of lakes in the north and a shallow marine sea in the south. And the exposures and the outcrops of the Bows Formation are represented by these yellow patches that you can see up and down the lower part of the Colorado River Valley here. And then the white area shows the area of latest Miocene inundation by lakes in the north and a shallow marine sea in the south. And so this is what we call the Blithe Basin. And the area where we'll focus a lot of our research is right here in the southernmost exposures of the Bows Formation near the town of Cibola. So now I'm going to tell you a little bit about the Bows Formation, which most of you have never heard of, but in some circles it's like a really important unit. And it's very, very diverse and inspiring geologic unit, sedimentary unit. And so this shows that the Bows Formation rests, it overlies older Miocene volcanic rocks and alluvial fan conglomerates. And I will note that it is overlain in turn by the Bullhead alluvium, which is begins at about 4.5 million years ago. So the Bullhead alluvium is going to correlate to that Arroyo Diablo formation that we just saw. So we have in between these two boundaries, the different members of the Bows Formation. And the Bows Formation includes a basal carbonate member, a siliciclastic member, and an upper bioplastic member. The basal carbonate member is a mixed carbonate siliciclastic unit that records deepening up in a tidal to subtidal environment. The siliciclastic member also is a very systematic coarsening up succession from claystone to mudstone to sandstone, which records the progradation and first arrival of the Colorado River Delta and river right there. And then the third member is really important, is the upper bioplastic member, which is records deposition in a marine bay that reflooded the lower river valley after the river first ran through it. And that's kind of the surprise of this talk. So I'm going to tell you about these different members of the Bows Formation and how they inform us of the early development of the river. This is a geologic map of the study area, just showing the general distribution of tertiary volcanic rocks and conglomerate, and then the Bows Formation is indicated in these this blue color here. And I'll show you results from the eastern side of the river valley and then the western side of the river valley, starting with a couple of nice studies by Brennan O'Connell and others in the western Trigo Mountains. And here we find that the basal carbonate member contains really a diverse set of tidal facies in a mixed carbonate siliciclastic system. We have marine fossils that include barnacles, bivalves, gastropods, and forams. And sedimentary structures include flazy, wavy, and lenticular bedding with dune cross bedding and coarse grainstone. We also see examples, lots of examples of sigmoidal cross bedding with tidal bundles and reactivation surfaces, and a variety of different ichnofacies, including thalassinoides burrows and camel tracks. And so this is a lot of other information. It shows a very convincing story of tidal sedimentation in a tidal straight setting. Now, if we go over to the other side, the western side of the river valley here, in the eastern Palo Verde Mountains, this is some work done by Kevin Gardner and myself. And again, we see the same mixed carbonate siliciclastic tidal facies, similar to what we saw on the eastern side. This is showing an example of herringbone crossbedding in these deposits. And especially exciting contribution by Kevin was that he worked up a lot of documentation and collected a lot of data from these compound dune crossbedding in grainstone, which represent the deposits of a subtidal dune field. So he recognized these the hierarchy of different bounding surfaces within this crossbedding and used that to understand both the type of bed form that he was looking at and the transport processes, as well as the paleohydrology and the water depth and so forth. So it's a very sophisticated piece of work. And so based on these different types of analysis, we have a basin model where we can look at the similarities and differences between the western side of the river valley, sorry, the eastern side of the river valley and the western side over here. And the basin model basically depicts a west tilted half graben basin that tilted to the west because of slip on a normal fault here. And that explains the presence of very wide, low gradient tidal flats that Brennan worked on the eastern side of the basin, which formed basically on a pre-existing hanging wall dip slope. And then over on the western basin margin, the tidal flats are much more narrow. There's really just a narrow little strip of tidal flats, and we see onlapping of carbonates onto rocky exposures. So it's a steep rocky shoreline, and that then both sides of the basin then saw a transgression through time. And so we can use that to develop a paleogeographic reconstruction for the base. We're still just talking about the basal carbonate member. And so you can see that this restores to a tidal strait, which was fairly narrow and has this interesting dog leg, but with the deposits that we see here near the Highway 78 pass, we can make a connection all the way through. And we then reconstruct that this was the setting of a funny fault controlled sort of jogged complex tidal strait that linked the Paleo Gulf of California in the south to a shallow marine basin in the north. Okay, now that's our reconstruction for the basal carbonate member, but remember that's overlain by the siliciclastic member. So now I'll tell you about that. And the siliciclastic member starts with a green clay stone, which is a very low energy clay unit that formed in a subtidal environment. It directly overlies, you can see in this photo, it rests directly on top of the youngest deposits of the basal carbonate member. And it is gradationally overlain by the by red mudstone and siltstone with weak paleosols and desiccation cracks. And that in turn is overlain by thick bedded, multi-story trough cross-bedded and tabular cross-bedded sands that form in channel networks, which represent a clearly deposition in a fluvial river channel system. So the siliciclastic member of the Bowles Formation shows a very systematic and predictable coarsening upward succession, which can be readily interpreted as the result of a prograding delta. And this was already interpreted as a prograding delta system by previous workers like Anna Busing and Kyle House and Phil Pertry have all interpreted this transition to be a prograding delta. I think that our contribution is to say, and the river really arrived at this time as well. So we can interpret this succession in terms of, transition from a pro-delta clays to channel mouth bars at a channel front environment like we see here, and then the transition right up into those big, large-scale multi-story cross-bedded sands of the Colorado River channel system itself. So this stratigraphy clearly records the first arrival of the Colorado River in the lower river valley at about 5.3 million years ago. And that age is based on our 4M biostratigraphy that Chris McDougall at the USGS has done in these deposits, as well as our correlation to the Fish Creek Vallecito Basin. So then that allows us to start reconstructing the system. We have data in hand. I've shared with you the highlights of our data, and now we're going to do sort of our regional reconstructions. And so this is from a paper we recently published in Geosphere, and it emphasizes the importance of the Paleo Eastern California shear zone, which we know is active today, and it turns out was active also in the east. An area which is now relatively inactive, but was active about 5 to 6 million years ago, is really where this deposition took place. And so what we can see is that the deposits of the Bowles Formation, we start with the basal carbonate member, and we look at this fault-bounded tidal strait, which connected the Gulf of California in the south with this larger inland sea in the north. And these deposits formed here because this was the locus of subsidence during that time. And in fact, that actually, the subsidence caused a deepening up and a transgression over time, right in this area. This subsidence that was completely fault controlled provided the pathway for the arrival of the Colorado River, which is recorded in the siliciclastic member of the Bowles Formation, and is also recorded in the Wind Caves member of the Latrania Formation that we looked at in the, so all the way down here at the bottom of this diagram is the reconstructed position of the Fish Creek Vallecito Basin at about 5.3 million years ago, because remember, we've had to undo all of that plate motion. So at that time, the Fish Creek Biocito Basin was down, all the way down here, receiving sand from a submarine canyon complex that was fed by the river with probably a small delta that formed here. So all of that would be fine. And it's a very, very solid conclusion that is based on the correlation of the Baus Formation to the Fish Creek Biocito Basin. But the thing is, what happened next is not expected. And this is the surprise of this presentation is here. What happened next is we now conclude that the Colorado River Delta retreated, okay, from here to here. It's really fun to go back and forth. More than 100 kilometers, it retreated and transgressed and backed up and backstepped all the way to the Parker area at about 5 million years ago. This event is recorded in the deposition of the Coyote clay, which is a regionally extensive sand-starved clay unit, and the deposition of the upper bioplastic member right here in the southernmost Baus Formation. And so the upper bioplastic member provides an important key for this moment in time, because I'm circling the area where we have really documented the upper bioplastic member. So we're going to go take a look at a few of those deposits, and then we'll come back to this regional picture. Okay, so the upper bioplastic member of the southern Baus Formation is the uppermost, and perhaps arguably the most important member of the Baus. In this representation, I'm showing how the upper bioplastic member, represented here, rests on top of Colorado River sandstone channel sands in the central part of the basin, but outside of the downdrop part of that basin, the Colorado River sand was either not deposited or maybe was removed by erosion. And so the upper bioplastic member rests directly on top of the basal carbonate member you see here. Basal carbonate member comes up, and then the upper bioplastic member rests directly on top of it, outside of that main depot center. And so that's a regional unconformity that has karst breccias and fissures and lots of important evidence for hiatus at that time. And the upper bioplastic member is also a mixed carbonate siliciclastic deposit. And importantly, it records reflooding of the lower Colorado River Valley up into the valley after the river recorded in these sands first ran through it. So in this figure here, I'm just showing an example of chevron wave-formed ripples in pebbly bioplastic carbonate, which clearly records deposition in a subaqueous environment. Other facies include water lane, wave rework, ripple bed forms in sandy bioplastic carbonate, and we have HCS-like cross-bedding in calcareous matrix conglomerate. And we've done a lot of facies analysis in these deposits, and we interpret that these large-scale convex upward cross-bedded carbonate conglomerate deposits probably formed from tsunamis in a restricted marine bay or estuary. The marine origin of this unit is confirmed with the common occurrence of coralline-like calcareous red algae, which is marine, as well as other marine fossils, including echinoid spines, which we never see in the basal carbonate member, barnacles, clams, and circulid worms. And so this allows us to reconstruct the history of river initiation and early evolution. So this is another perspective, another way to look at it is kind of a perspective diagram looking sort of up into the lower Colorado River. And starting between 6 and 5.5 million years ago, the basal carbonate member accumulated in a fault-bounded tidal strait, as we've already seen, that connected the Paleo Gulf of California in the south with a larger shallow inland sea in the north. And starting about 5.3 million years ago, the siliciclastic member of the Baus Formation formed here in the lower parts of the channel and very quickly prograded through, created a delta, and deposited those submarine sands of the wind case member down in the Fish Creek Biocito Basin. And then at about 5 million years ago, the delta retreated and it backstepped all the way up into the Parker area. This is greater than a 100-kilometer retreat of the delta. which resulted in the deposition of the upper bioplastic member here in our former tidal strait setting. Now, just if you're curious, I have a couple of stratigraphic panels. Panel D goes from sort of southwest to northeast, and then panel E goes right across the basin here. And this is panels showing schematic stratigraphic architecture to illustrate how in panel D here, the upper bioplastic member rests directly on top of those older Colorado River channel sands, and we infer that is laterally equivalent to the sands in the Parker area, which accumulated in a transgressive bayhead delta. And then panel E, which cuts across from west to east, is shown down here. And this is just another way to emphasize the fact that that sedimentation took place in a tectonically downdropping subsiding basin. And outside of that downdropped area, the Colorado River sands were not preserved, so that the upper bioplastic member rests directly on top of the basal carbonate member. And so that's our evidence for the retreat and the backstepping, the surprising controversial backstepping of the delta at about 5 million years ago. So we might really, that might lead us to the next question, is what caused the backstepping and retreat of the Colorado River Delta at about 5 million years ago? And here I'm using a figure from our 2021 geosphere paper to just emphasize the role of the Eastern California shear zone. And so here you see it's this whole zone of transitional deformation east of the San Andreas Fault. And the pink area highlights the modern Eastern California shear zone, which is known to have a number of modern ruptures, historical ruptures that have created quite a lot of news. And is actively deforming, is where most of the geodetic motion takes place, right through this red band here. And then over on the eastern side is what we call the Paleo Eastern California shear zone. That is, it's relatively inactive now. There's almost no GPS plate motion, and there's no modern ruptures, and it's relatively structurally inactive right now. And here's where the delta parked. After making it all the way down into the Gulf of California, it retreated up to this position here. And so the question is still sitting there: what caused the backstepping and the retreat of the delta? And we proposed that a pulse of strike slip normal faulting in Death Valley and the greater Eastern California shear zone was responsible for this event. And so it turns out that it's very difficult to date these events with stratigraphy, but in the Death Valley region, because so many people work there, that they actually have discovered evidence for an important pulse of tectonism about 5 to 6 million years ago, with evidence from faults in the structural evolution of the Furnace Creek Fault Zone, thermochronology in the Black Mountains. There's a footwall of one of these major normal faults, and syntectonic deposits in the Copper Canyon Formation. So that's where we really have some information about the timing of this event. But this was not an isolated event, because if we start moving that transtensional system in these faults in the Death Valley area, it did not only happen here, but those faults were linked to the regional faults of the Eastern California shear zone, which had the Colorado River embedded within it. And so we have proposed that this faulting episode, which is dated in the Death Valley region, really affected the whole Paleo Eastern California shear zone, and it had two major effects. It resulted in a rise in relative sea level as a result of tectonic subsidence in this region, which is recorded in the very impressive transgressive ravinement surface at the base of the upper bioplastic member. And we propose it also resulted in a decrease in the river sediment discharge as a result of subsidence and sediment trapping in these upstream basins. And that's sort of the concept we talked about earlier. And again, that concept is, if we have a zone of active faulting and subsidence, and there's a river embedded within that fault zone, then as the river moves down through that fault system, then the sediment trapping will actually force extraction of the sediment from the discharge, and that can theoretically cause a significant decrease in the sediment discharge in the downstream direction as a result of sediment trapping, as we saw earlier. So really the question is, then did that really happen? And we need to look at the potential sinks or traps for that sediment to see if there's enough volume available in those basins to potentially hold that sediment over that period of time. So we'll look at that next. And so here's a close-up of that area, just looking at the potential sinks within fault-bounded sedimentary basins here along the lower part of the Colorado River Valley. And the potential sinks include, but maybe are not limited to, the Cottonwood Basin, the Mojave, Chemehuevi, and Parker Basin. And so first we have to ask, how much sediment do we think might have been delivered from the Colorado Plateau, the upper part of the river, that we have to hold in these basins? And we can calculate that using our early Pliocene paleo sediment discharge, which earlier was calculated about 3,750 to 10,000 cubic meters per million years. And we need to know the duration of the sediment shutdown, which was anywhere from sort of 100 to 300,000 years. And we expect that the river, the upper river feeding into this area, might have produced a total sediment volume of about 375 to 3,000 cubic kilometers. So what does that mean? And can these basins even hold that amount of sediment? And so what I did is I've been through measuring the area of these basins as well as their likely depth, and we have some evidence of stratigraphic thickness from around the margins of the basins. And there's also a really nice study in the Mojave Basin right here by Saltis and Hawkins. With the Mojave Basin is a 3-kilometer deep basin. And what I've done is just done some very simple calculations using the area and the average thickness of the sediment in these basins, including a minimum and a maximum. And with a minimum, I use only like 500 meters of sediment, even though I know the Mojave Basin is 3 kilometers thick. So I'm trying to find a minimum and then kind of a reasonable maximum. And by just bracketing what I think are minimum and maximum values, then what I find is that the volume of sediment, which is of similar age within the basins, can be estimated at roughly 760 to a little over 3,000 cubic kilometers. And that's very similar to the volume of sediment that I estimate was produced by the upper part of the river during that period of time. So while this is not an absolute proof, it's the sort of next step in this analysis, which is to show that the sediment trapping hypothesis is reasonable, and it's supported by this very simple mass balance analysis. And so it passes the plausibility test. So finally, then we can talk about the controls on regional river delta over time by correlating the deposits in the lower Colorado River Valley here with the equivalent deposits in the Salton Trough in this column, and then we can correlate both of those to of global sea level change from Miller et al. 2020. And so what I've done is I've taken our measured stratigraphic sections and converted them to time diagrams, chronostratigraphic diagrams, to look at when things were happening at different times. And we start with a transgression that resulted in deposition of the basal carbonate member, as well as these turbidites down in the Salton Trough. And this was and we'll try to explain shoreline shifts. The first major shift is the transgression that flooded the whole lower Colorado River Valley, as well as the entire Salton Trough region. And that's clearly the result of tectonic subsidence, which is documented in many other studies. So clearly tectonic subsidence along the plate boundary resulted in the flooding of marine waters up into these fault-bounded basins. Now, the next important shoreline shift is the major regression that got the Colorado, initiated the input of sediment that drove the Colorado River and the Delta all the way down to the mouth of the river and delivered sand.
Il 13 giugno non ci sto.
The Basilicata Basin. And so this is our initial sediment flux.
No, qua c'è una conferenza di servizi il 13 giugno, non ci sto.
Okay, well, I will not be distracted, because nothing can distract me. So we have now the initial sediment flux, which this is a whole separate subject that I haven't really gotten into yet, but this can be understood as a result of climate change, which was becoming more wet and with increasing rainfall during latest Miocene time, which ultimately resulted in the spillover of lakes from the Colorado Plateau, which has been documented by Kyle House and other colleagues who show that it was really the whole Colorado River initiation was a series of top-down lake filling and spilling events that delivered that initial pulse of sediment all the way down from the Colorado Plateau, all the way through the valley down to that could be potentially attributed to climate change at that time. Then we have the next event, which was surprising, which is the transgression and the retreat of the delta all the way back up into the lower river valley. And as I just showed you, we attribute that to a combination of tectonic subsidence, as well as a significant decrease in the sediment, the river sediment discharge at that time. And they both would have the same effect of driving that delta back up into the river valley. And then, yes, this is my concluding statement, and the thunder comes. I'm just so grateful for the timing. And then, and then finally, we have another shoreline shift, which was at the end of that transgressive period. The delta migrated all the way back out, and that's what ultimately culminates in the arrival of the river sedimentary environment in the Salton Trough and the Arroyo Diablo Formation, as well as the Bullhead Alluvium, which fills the Colorado River Valley with very thick sections of river sediment. And that increase of sediment flux is still not very well understood. It could be a result of say river captures occurring in the up on the Colorado Plateau, although there's some evidence that would argue against that. There could be, the system could have been working toward achieving some kind of equilibrium between flexural uplift and erosion over time. So there are different ways to explain why the discharge was relatively, so we had relatively low paleo sediment discharge during this time, which allowed that transgression to happen. But then the subsequent regression is the result of a huge increase in the sediment flux at that time. Now, what we can say is that global sea level was not a major factor in these changes, because we can see on this plot on the left that there was little or no change in global sea level during that time. And any changes that might be pulled out of this are actually working in opposite to the direction of the observed shoreline shift. But what we do have is a record of extension and subsidence in the Death Valley region and the greater Eastern California shear zone at about this time. So we propose that this tectonic subsidence and trapping of sediment was is the best driver that we can find to explain this surprising, unexpected transgression recorded in the upper bioplastic member of the Bowes Formation. So I'm wrapping it up here. I have not kept track of the time, but I hope I haven't gone too long. We have a really nice record of highly unsteady punctuated sediment discharge during the initiation and early evolution of the Colorado River. And especially the retreat of that delta is unexpected and still a little controversial. But we have good evidence that these major excursions and back and forth migration of the delta, this large river delta, were a combined kind of consequence of tectonic subsidence and trapping of sediment in those basins, which actually is very similar to the sediment trapping that has been produced in the modern day by the capture of sediment in the dams and reservoirs today, which resulted in a 3 order of magnitude decrease in the sediment discharge just since the early 1900s. So it's really fun comparing those two timescales. And then finally followed by the bigger increase of sediment discharge. So it's just one example of tectonic controls on river initiation and evolution, which has taken a long time for us to figure this out. But we think that this should be an important process for the evolution of continental scale rivers in other tectonically active settings as well. And I will stop right there and really appreciate your attention and very happy to answer any questions. Thank you so much.
Thank you, Becky, for this brilliant presentation. And I will ask if there are questions from the audience here in person, and eventually from home. For the online participants, I will ask them to write eventually the question in the
yes.
chat window. Thank you.
We could hit, if we hit the escape, will we be able to see the chat window?
Yeah. No, I can read. I can.
Oh,
read.
you read there as well.
I can
Okay.
read the chat here.
Very good.
Are there questions here? Yes, Fabrizio.
Well, first of all, thank you very much. You're a terrific speaker, and I learned so much today. So thank you very much.
Thank you.
Actually, I really apologize that I didn't have the chance to meet with you earlier.
Oh, yeah, well, we're still here.
Many things to know. Well, I took some notes, and actually I have just a curiosity and then 2 questions.
Yes.
The curiosity is that you talk about straight partitioning in order to justify lumping and bilateral on the Andreas Fault. Could you better explain this concept to me, please?
Well, yes, the idea is if you have a plate boundary with a known orientation, it's like this is going to be the orientation of the plate boundary. But then we have the relative plate motion. And if the relative plate motion is perfectly parallel to the plate boundary, then that's great. You'll just have a strike slip fault. But if the relative plate motion is oblique to the plate boundary, then you have sort of 2 choices. And this concept was developed by Stock and Hodges like a long time ago, and Spencer and Normark before that. It's a really important concept that for say a strike slip or a transtensional plate boundary, your 2 options are either to, well, you can actually have 3 options. One would be just the whole thing would just be oblique slip, or you could partition the strain into a component that's parallel to the plate boundary, which would be your strike slip faults, and then another component which is perpendicular to your plate boundary. And so in many fault systems, apparently, as I understand it, strain partitioning or sort of segmentation of the strain field into those 2 components does take place.
But the question is why low angle fault? Because it would have been justified with high angle fault.
Yeah. So
really
absolutely. So now we're talking about the extensional component of that partition strain. And the extensional component could be either on high angle faults, high angle normal faults, or low angle normal faults. And what we did is previous workers before us went and discovered that actually this was a low angle normal fault. And so when a region is undergoing extensional or transtensional strain, it needs to decide if it's going to deform on high angle or low angle normal faults. And the rule of thumb for that is that regions which have hot crust, thick crust, and rapid extension. Yes, thick, hot crust, and rapid extension. So 3 components: fast extension rate, thick crust, and hot crust seem to be the physical parameters which favor the development of low angle normal faults. And if you have cold or thin or crust or slow extension, then you might be more likely to create high angle steep normal faults. So that, I mean, I can give that to you in a sort of a neat little bundle. There's really a lot more to discuss, but maybe I'll try to stop there.
Yeah, I have 2 questions to you in order because I really like your models. And the first question is, what evidence of thin sedimentary faulting have you found in order to support your 3D model for the vesicle carbon? Because I haven't seen any.
Yes, and I did not present that because, as you noticed, I already spoke for an hour.
Okay.
I could go on and on. But I will spare you. But what we found in our 2021 paper, which is published in Geosphere, so it's really easy to find, is that we actually have really important evidence from stratigraphic architecture, which shows the presence of basically wedge geometries and onlapping and offlapping stratal architecture, which provides evidence for tilting during deposition of the basal carbonate member. And we see that actually on both sides of the basin. And in one place, so first of all, I should say that when we see this kind of geometry in an extensional setting, often that results from, as Rob Gothorpe and Leader and many other people have shown, is that those kinds of monoclines often form above the tip of a propagating normal fault. And on the eastern side of the basin, we actually see that fault, which propagated right up to the surface and then resulted in tilting back toward the fault. On the western side of the basin, we see the same kind of geometry, the tilt wedge and the growth structure, which is very clear evidence for tilting during deposition of the basal carbonate member with the very same geometry, except that fault seems to have not quite made it to the surface. Okay. So what we have is a tectonically active basin, but during that time, that apparently it stopped, the fault tip stopped, but it left behind this really distinctive diagnostic wedge, this growth structure. So we have growth structures in the basal carbonate member, which provide the evidence for syn sedimentary control on tectonic subsidence. And I refer you to our geosphere paper to learn a lot more about that, because that paper is entirely about that question. Yeah.
Absolutely.
Right.
Thank you very much. And that brings me to my last question about you talked about cross tension. So I wonder if you have any magnetic data you were referring about that actually are consistent with rotation on the vertical axis.
So I should say that Bernie Hausen at Western Washington University and his students over time did a lot of work on the paleomagnetic data and analyses. He's the absolutely first-rate lab, a great guy. And they looked for, there's some rotation in the Fish Creek Vallecito Basin, but not that much. And so like the paleo currents that I showed you, a bit of clockwise, but it's weak. And, it's very hard to get a really clean signal of rotation, even with very good data, because a lot of the samples actually came from like cemented siltstones and things, because the muds like really fall apart and so forth. And so he got good data for doing polarity reversals, but it was harder to get really concrete results on rotation. But the best that he got, which is pretty good, but I'm not sure if it ever appeared in any published papers, was that there's a bit of clockwise rotation in those sediments of the Fish Creek Vallecito Basin. Not a lot, maybe 10 or 20 degrees. And so then the paleo currents that I showed you, for example, for the wind caves member, actually had adjusted for that, had removed that amount of clockwise rotation. It's not that much. So interestingly, I mean, there's some places along the San Andreas Fault system where it is like 90 to 120 degrees of clockwise rotation, like in the eastern transverse ranges have like really swung like that. And actually there's so much rotation that it contributes to a significant percentage of the relative plate motion over certain periods of time. Just on the northeast side of the San Andreas Fault, there is a lot of that over time. But interestingly, in the Fish Creek Vallecito Basin, where this study was done, it was relatively little. Yeah, you're welcome. Thank you for your question.
Other questions?
Hey, Becky.
Hi.
Can you hear me?
Yes, hi, Paul.
Hey, thank you for this fantastic talk. It's a great story. And one question you mentioned about 5 million years ago, that backstepping, the retreat of the river mouth and the delta shifting to the eastward. Yes. And here, as we all know, the Gulf California, the Gulf formed 10 to 5 million. So it's very interesting that at 5 million years ago, you mentioned possible subsidence in that area, in the delta area. So my question is, how about the Baja California Peninsula? Because that peninsula most likely emerged from the ocean at around 6 to 5 million years around that time. So how much the uplifting of the Baja California, contribute to the overall? This could be create a tuning up or push the subsidence of Backstepping Basin. Make the sea level rise, make the river retreat.
Absolutely. Yeah, that's a really neat question. And I didn't really talk about the Baja California Peninsula again because of just the time constraint, but we've thought about that a lot. And first of all, I should say that the arc volcanism in that region ended by about 10 to 12 million years ago. So everything that happens after that is not really a back arc basin. Maybe was at one time, but starting around 10 million years ago, then it began to really feel the effects of the strike slip plate motions starting to fire up in that area. What we do have, like in the Santa Rosalia area, we do have evidence that the Baja Peninsula was being uplifted, started to be uplifted at about 8 million years ago, perhaps 6 million years ago. There is a history of uplift in the Baja Peninsula at the same time that alluvial fans and fan deltas were building out to the margin of the earliest Gulf of California. And that would actually be at about 6 or 6.5 million years ago in the Santa Rosalia area. But there are very few really good studies of deposits of right that age coming off of the Baja Peninsula. But there are a few other paleo basins of that age which support that same kind of setting. That is, the peninsula was starting to acquire kind of its current form by about 6 to 6.5 million years ago, because we do have deposits that represent the edges of alluvial fans and fan deltas that were prograding right into those earliest waters of the Gulf of California. So I don't know if that really answers your question. Let me try just say one more thing about that. There's a really important paper by Paul Umhofer et al., which is published in 2018, which is in a geology paper. And you might check that because it helps to illustrate what I don't have time to really summarize here, but that there's a really nice record of the breaching of strike slip faults by strike slip motion through time that progressively flooded marine basins northward along the plate boundary, which resulted in the formation of the Gulf of California by about 6 million years ago. It was a big, long, skinny marine seaway that was very long and skinny by 6 million years ago. And at that time, then the Baja Peninsula probably by that time was a long, skinny peninsula next to that long, skinny seaway.
Super good. Thank you very much.
Thank you.
Thank you, Paul. Other questions? Also from home? If not, I have just a question, Becky.
Okay.
Well, I was impressed by such huge erosional surface at the base of the bioplastic member, upper member of the Boost formation, which is a transgressive surface.
Yes.
In a way. So we proposed a couple of years ago a new type of tidal remnant surface related to the onset of straight sedimentation. And the major, let's say, difference between the classical remnant surface is that on top of the surface, there's not any extraline deposits or parallel deposits, but they are open sea and deep marine or relatively deep marine straight deposits. So in a way, it is an energetic surface that can assume also huge proportions at the basin scale. So my question is if this kind of surface may be related to some straight tidal remnant surface at that time.
Yeah, that's a great question. And, we've thought about that, and I don't think we fully understand that surface. What we can say is that it does record a period of exposure. We have some nice, so that is an unconformity that records a low stand. There was exposure and development of karst fissures and karst breccias along that surface. And then directly on top of that are just mixed carbonate siliciclastic facies. And without any really significant relic deposits of, say, the Colorado River sands. So we just jump from the older river sands into this new, we'll call it a marine bay. And it could have had a tidal influence, but the puzzling thing is that the deposits directly above that surface do not really have any compelling evidence for tidal influence. So, occasionally we see a little wavy or flazer or, lenticular bedding, or sometimes we think we see a little bit of rhythmic layering, but there's nothing really convincingly tidal the way we saw in the basal carbonate member. Instead, it just looks like an energetic marine bay. So it's certainly a marine transgression, and it certainly cleaned off that surface, and it certainly is a ravine surface.
So basically, erosion was due to wave action.
Probably, I guess, probably with wave action. But I say that mainly just because we don't really have convincing tidal facies in the upper bioplastic member. But it's a very interesting question because you have to think about the balance of sediment delivery or lack thereof, and then the energy occurrence in the basin. And then the best evidence we have is what the deposits we see on top of that, which is a variety of waveform, ripple bed forms, and some HCS-like structures. And but it's still kind of a puzzling question,
Or sometimes the same surface at Basin scale, may assume different, let's say, identities.
Absolutely. Well, tidal influence could have ripped right through, but then the record that got left behind was did not have a very strong.
But one of the diagnostic elements to eventually identify a tidal straight revenement is the presence of large cross beds, indicating that erosion at that time during the transgression was doing dominantly from straight by straight.
We have some interesting long wavelength crossbedding, but it's never sitting right on the basal surface. It's always up in the section.
This would be one of the theories.
Right.
Thank you very much.
Right. Thank you.
Okay. Other questions from the audience? Okay, if not, I would say thank you very much
Well, thank
to
you.
our speaker, Becky Dorsey, University of Oregon, here as a visiting researcher at University of Basilicata for a couple of weeks, unfortunately. And thank you also to the audience. Thanks for coming, and thanks also to the online participants for coming. Thank you very much. And